So our next lesson, we're going to expand a little bit on what we did in sections 4K, 4L, pretty much all of chapter 4. And we're going to look at the derivative and how we're actually going to use this. Because up to this point, we've essentially just been learning the rules and doing a lot of memorization and technical skills and simplifying and things like that. But I want you guys to start seeing how we can use some of the derivative information that we've been using the last 2 weeks, 3 weeks, month. And so just to kind of revisit what it means to be a derivative or what the derivative of a function is. So first and foremost, the derivative is the slope of the line tangent to a function at a given point. And we've done that quite a bit where you are finding the derivative, plugging in an x value to find the slope of that line, and then writing equations of tangents and normals. And again, a lot of the procedures that we've been working on the last few weeks. The second, get rid of that. So the second thing we talked about the derivative is it's an instantaneous rate of change. So you look at a function is what is the rate of change at that specific moment? And that's what the derivative finds for you. So the instantaneous rate of change. And a third way is at any given point is how much is the y value changing with respect to x? And essentially that is just slope. Remember, slope is just rise over run, change in y over change in x. And so what we're going to do to expand on that a little bit is what actually does the derivative do? And so what we want to think of is another way to think about is the behavior of a graph. So for example, if you find the derivative and you plug in an x value and you get a derivative that's positive, what does that actually physically mean for a graph? Well, we say when the derivative is positive that our function is increasing. So I want you to imagine that you are on a roller coaster and you're moving from left to right. Is what is the movement that's actually going on as you pass a particular point? And so if the derivative is positive, as it is right here, we say that a function is increasing. And then what happens if you're going the other direction and you're going on the downswing? So if the slope of the tangent line is negative or the derivative is negative, we said the function is decreasing. And then lastly, what happens when we hit these peaks and valleys? The slope of the tangent line is 0, so we say that the graph is stationary or constant at a particular point. And so what we're going to look at is a little more than you guys did in Algebra 2, where Algebra 2's focus was on finding the x-intercepts and exploring this end behavior. We're now going to start digging into a little bit of where are these peaks and where are these valleys and how do we find them. And so the first slide here, and I'll give you guys time to copy these down. So if you want to pause the video and you can write this down, we're going to look at things that are called stationary points. And I want to go back to Algebra 1 and Algebra 2 when you guys first learned about x-intercepts. And there were a lot of different names for x-intercepts. We called them x-intercepts. We also called them roots. We called them zeros. Again, I apologize for the handwriting. It's very difficult to write with a mouse. So we called them roots, zeros, and we also called them solutions. But these all meant the same thing. So if you were finding the roots of a function, you were finding the x-intercepts. If you were finding the zeros, you were finding the x-intercepts. And so in calculus, we have these things that are called stationary points, but there are a lot of different names for them. We call them extrema or extreme points. We call them turning points. We call them critical points. Sometimes we call them critical values. And so these two specific ones we're going to focus on are maximum values, which we'll from now on just call maxes, and minimum values, which we call mins. And we explore the behavior, similar to what we did with limits, of what happens on either side of these particular values. So you notice a maximum value is a peak in a graph. And the way we define the peak is on the left side. So as you move from left to right, you are increasing up to this specific point, and then it flattens out, and then it decreases. So any one of these stationary points or turning points where you increase, flatten out, and then decrease, we call those maximum values. And then on the flip side of that, what if we have something where you are decreasing, and then you flatten out, and then it turns into increasing? We call those minimum values. And so how do we formally define what these are? Again, feel free to pause the video at any point in time to write these down. because these are fairly important for any calculus class. And so how do we define what a minimum value is? The first thing you need for any minimum value is you find the first derivative, and the first derivative is equal to 0. Again, what does the first derivative tell you? Well, it tells you the slope of the line tangent to a curve at a given point. Well, if the slope of a line is equal to 0, we know the only types of lines that have slopes are horizontal lines. And so first, you must have the first derivative equal to 0. And then for it to be a minimum value, again, think of this as a roller coaster moving left to right. We know that any values to the left of this particular value, so in this instance, we're talking about C, we'll call this value C. To the left of C, we have a function that is decreasing, and then at C, it flattens out, and then greater than C, it increases. And so that's what this information says, and we'll color code it a little for you here. So the red tells us that the first derivative is equal to 0, which we have right there. The second part is when you're less than C or to the left of C, the first derivative is less than 0 or negative. So that tells us that the function is decreasing. And then to the right of C or greater than C, we have a derivative that's greater than 0 or positive, which means it's increasing. Similarly, to define maximum values, again, pause the video to write this stuff down, fairly important, is you have a similar setup. For something to be a maximum value, the first derivative must equal 0. So at this value, we have a slope of a tangent that is equal to 0. But the subtle change here is when x is less than C, so this is C, when x is less than C or to the left of it, the first derivative is greater than 0, which means the function is increasing. And then when x is greater than C to the right of it, we know that the derivative is less than 0, which means it's decreasing. And so just to kind of summarize those two slides, is stationary points. And again, we identify these potential points by finding the first derivative and setting that first derivative equal to 0. Once we do that, we look at a number line and we explore what is the behavior to the left of it and what is the behavior to the right of it. And this is very, very similar to what we did with our critical values or our fence values when we were solving inequalities in a previous unit. And we'll go ahead and call that the end for number 2, or for video number 1, and we'll do second video to show you guys some examples of how we actually use this.